Dobro jutro, Belgrade. That's as much as my Serbian goes, unfortunately, so I'll stick to English now, if you don't mind. So yeah, my name's Gerald Venzl. I'm a product manager for Oracle for the server technologies, fancy name for the database technologies that we have. And today I'm gonna show you 10 tips and tricks to tune your SQL or your databases. Now, the first thing to mention here is that we're talking about performance, and keep in mind that everything I'm going to demonstrate to you is running on my tiny little laptop over there, and I tweaked it in a way that it's demonstratable. So I made it slower than it usually is. So don't just take the numbers one for one, take it back to your companies or back home, and also don't just say Gerald said we have to apply this everywhere. Common sense in IT always applies. Please use it. There's way too few people these days that use common sense in IT. Now, before we get started to those tips and tricks, first I want to cover what is actually performance. So before my life in Oracle, I was a performance engineer. I spent a couple of years tuning systems, all the way from the OS up to back then J2E applications. And of course, databases were in there somewhere as well. And I came up with a very simple formula that let me figure out whether or not the expectations were realistic or not. And so I would like to share this formula with you. So if you want to put something against what's performance in an equation, it will be as simple as latency times throughput. So latency will be how long does it take to process one given item of work, whatever that may be, your business transaction, a database transaction, complex calculations, etc. It's a unit of work that you define, and it will take some time to process. The important thing is that the unit of work is either being processed on CPU or it's waiting, which we usually call I/O. That could be disk, that could be network, but also waiting for other things or just being idle. And the idea or the goal is to process this unit of work as efficient as possible, right? So we want to complete this as fast as possible so that we can process something afterwards as well. Important thing here is that we also want to free up resources as fast as possible so that we actually allow other work units to use those resources. So the typical free up memory when you can, don't spend CPU cycles unnecessarily, and so forth and so forth. Throughput is just simply how many you can process in parallel. Very simple, very easy. So if we want to take this simple equation and I'll say how many, if we want to process 10,000 work units per second, what does this equate to? So we have 10,000 of something that we need to process in a second, let's say business transactions. Well, it could be something as simple as saying if our latency is 1 millisecond, we can process 1,000 in a second. That means we have to be able to process 10 work units in parallel. If we don't achieve this, you never get to your 10,000 per second. As simple as that. Now, of course, 1 millisecond latency is always very opportunistic. You not always get that performance. So sometimes latency just takes longer, right? So what if it takes 10 milliseconds? Well, then you have to be able to process 100 in parallel. It's a very simple equation. Why I share this with you is because we had some horrendous or funny, I suppose, performance numbers where they said, oh, we need to be able to process 10 million transactions per second on a 2-core system, 2 CPUs, right? It's like, yeah, well, will never fly. If you just apply that, if my managers would have just applied that, they would have figured out it will just never fly. So maybe something for you to take home. The other thing I want to quickly go through about are the working states of databases, because actually, how many people in here are Java developers? Good. Like Python developers? JavaScript? C, C++? Go? Doesn't really matter. The good thing is that everything I show you today actually applies for all programming languages because databases work with all of them. But I show Java code, and I think I saw the majority of Java developers. Now, we developers usually treat databases as, these nice little black boxes, right? We toss the SQL over, and then the database is just slow, and then we go, oh, it's slow. We have no clue what's going on in there, right? And here's another little tip and trick that helps you already to figure out actually what's going on the other side. Of course, we could go for a whole hour into this nice debate why DBAs and developers hate each other, but let's not waste time on that. Now, databases themselves are very binary systems, as we have in IT. They're either working or they are waiting, right? So if we just keep it as simple as that. So working means we gave the SQL over, it processes over there, something's going on. Waiting means we do something processing in the application, and the database is doing nothing. And it gets really funny when the application is doing nothing and the database is doing nothing. But that's usually when we then blame the network guys. And luckily, there are no network admins around anymore. So we kind of all just agree that it's a network and move on. Funny anecdote there. Hopefully, some of you can smile on this and had this before. Now, actually, when you look in the database, once we have figured out that the database is working, right, so we gave the SQL over to the database and it's running, well, then actually it's very simple to figure out what's going on in the database as well on a very, very high level. The database itself is either busy processing your requests. That usually means it's running on a CPU or on many CPUs actually in databases, right? They're highly concurrent multi-processing systems there. Or the database itself is waiting on usually subsystems like I/O, disks, just not fast enough disk, or sometimes the network, right? We just don't get data fast enough to the database or from the database, or sometimes also just the user. Like the typical, somebody else updated a row, and you want to update the row, and the guy didn't commit the rollback yet, so you wait for his transaction to finish, because we have ACID transactions. Now, why do I share all of that with you? Because if you just get over to the database side, you very quickly find out is actually something going on or not that helps you troubleshoot a little bit more. Simplest thing I always did is I just looked at a top on the application server and a database server. Top is a Unix command that just shows you the CPU utilization. If there's no utilization going on the application server and no utilization going on the database server, something's wrong, something's off. Right? There could be some ACID transaction locking going on, but it could also just mean that you have a bottleneck somewhere from getting data to and from the database. Now, with Oracle, actually, if you happen to use an Oracle database, and I mean the Oracle database, not necessarily MySQL, but that's a great database as well. We actually track all of this since about 2000. So I just want to briefly share that, because if you have one of the Oracle databases, you can actually see exactly what's going on behind the covers. So whenever we are busy and running on CPU, we track that in something that we call statistics. Those are just incrementers of operations that we do on CPU. And whenever we are waiting, we track this we group this into wait classes and track this as wait events. To give you an idea, there's 2011 statistics in the Oracle database, in the latest Oracle database, so 2,000 different statistics on what operation we execute on CPU. It's quite sophisticated tracing that most applications don't even have. And then we have 13 wait groups, where we just group together, wait classes where we group together those wait events. And so you will see something like I/O, user I/O, or concurrency, or network, or commit, and so forth. And we have 1,884 of these wait events where we tell you exactly what the database is waiting for. So, just a real quick primer into databases, figuring out performance, and so forth. I hope this is helpful. Now let's go into the 10 tips in 45 minutes, or 40 minutes. So we have to go through a couple of them in an accelerated pace. The first thing I want to mention is round trips. It's something that we tend to forget. It's something that's obvious, but we still yet forget it. It's like the more round trips you have from and to the database, the longer you will wait on the network for this to happen. And what's not so intuitive for us developers is that sometimes it's actually better to have one network round trip and pass a lot of data over to the database side or from the database side to the application than have many, many tiny network round trips. Networks, even good ones, they take about a millisecond up to 3 milliseconds. That's still very fast. But again, this adds to your latency of processing a work unit, so we want to reduce this. So sometimes you get much more performance if you have a bigger pipe and you get more data over in one network round trip than have many network round trips. And I'll come back to that just in a second. But one other thing that means is that there's this religious debate going on whether you should do any processing on the database side or whether you should do any processing on the application tier. The DBAs would be like do all the processing in the database. The developers would be do all the processing in the application. My stand is do the processing where it makes most sense. If you have 50 terabytes of data in a database, you probably don't want to get every row out and do some basic calculation on the application tier, because you will pull 50 terabytes over the network, and you will mostly wait on the network. Yet, if you have complex processing going on the application tier that doesn't necessarily require a lot of data from the database, why would you not use the CPU processing power on the application servers over there? So, you know, apply common sense, as I said before, and just be open-minded of where to process things. Now, the second tip is actually commits and auto-commits, and this is where we'll step up here. I have prepared some live demos, so hopefully this will still work. So, and this goes back into round trips. So a general misconception is that people believe if I insert one row into a database, I have to write to disk. I have to write this row to disk immediately, which is not quite true. Every database actually puts that data into a memory area, into some sort of cache. We call it buffer cache. But when you commit is actually when we write to disk. This is when you say your transaction has been finished, you have ASIC guarantees, we make sure that when you commit, it actually hit the disk. Now, commit is a 6-letter word. For us Java developers, very, very easy to just call .commit and off we go. Or in Java, even more evil, auto-commit is turned on by default, so the driver will commit for us all the time. Now behind there's a couple of things that databases have to do. Not necessarily that you have to know all of them, but just to show that there's work to be done at a commit, not necessarily something as simple as say checkbox and we are done. So in Oracle, we would first generate something that we call SCN, a system change number. We would then write this redo, this transaction journal to the disk, to files called redo logs. We would then release the logs on the table, so you know any log that you have on a row that you just updated and so forth, we would release that. We would remove save points, we come to them in a second. You have save point guarantees as well, and then transactions within databases. And then we will perform potentially a commit cleanout and mark the transaction complete. So altogether, 6 steps that happen in a commit. One picture right there. And 2 of them will hit the disk, and the second one is optional. It does not always occur. Now, the trouble with commits, and especially auto-commit, is that, so auto-commit means the driver on your behalf will commit for you for every DML that you do. Every insert, update, delete, merge statement that you execute, the driver will automatically just do a commit for you. That has a couple of implications. Number one, every time you do a commit, you have a network round trip. Right? And we will see this in a second, how much overhead that actually is. You will also tell the database to write this one insert that you have just done to disk, although you don't necessarily have to. You may just be able to put many, many rows into this memory area first and then tell the database to write to disk once rather than many, many times. And of course, it also means, not to forget, we have ACID transactions, but if you have auto-commit turned on, your rollback is out of the window. If you ever want to roll back, you cannot do because your driver already auto-committed for you. So, in my opinion, I still debate with our JDBC standards guys. Auto-commit true is the default, and the JDBC specification, in my opinion, that's a bug. But hey, we're not going to get it changed, so make sure that auto-commit is turned off. Now, here's a practical example I want to show you. Very simple. We're going to do now a simple insert into a test table with 4 columns, and we're going to insert 10,000 rows, just in a for loop. Very ugly, just put there. And then we will insert a row and commit a row, and then we will do the same thing where we commit outside, right? So we insert 10,000 rows, and then we will just commit this at once, and we will track the time before and after. So literally 1 line of code change. Let's hope that the demo environment is still up. This looks good. So in here, oops, this is exactly the code that I have just showed you. So here we have this commit every row, insert into statement. The commit is in here. And then we execute the same thing again with the commit outside. We track the times. Now the other nice thing that I have here is a little monitoring tool that a colleague of mine wrote. Let me get this down here. That will show us exactly what's going on the database. We actually leverage those statistics and weight classes that the Oracle database gives us. So here we go. We go to this class, we execute, we have this 10,000 rows being executed. We see it down here. And so what we will see now here is what's happening on the database side, right? And so we see that we have essentially one session, that's one connection, I just do this in one connection, and we execute those 10,000 statements, and we see already that half the time we spend on CPU, that's great, half the time we spend on something that's called log file sync, this orangey thing. And this will take a while, and log file sync is exactly the event that we track for writing these redo journals to the redo logs. So for exactly you commit and we write to disk, and then once we have written to disk, we say the transaction is complete. So we wait for disk here mostly. We're finished, we wait 5 seconds, and then we execute the second one. So this took 34 seconds to execute. Here we go, we're already up and running. And you see that now we just have 100% CPU utilization. The log file sync is completely disappeared, and it finished in 14.3 seconds. Right? So that's the difference, just to give you an idea, between having the commit inside the loop and outside. We basically, the first time, we forced the database for every tiny little piece of data, there were only 4 columns, that's not a lot of bytes that we write, that it writes it to disk, while afterwards we said, okay, just put all of this in your memory structure and then write it to disk at once rather than 10,000 times. Oops. There we go. Demo. So now that's really nice, and so we just tuned our system from 34 seconds to 14 seconds, so we improved by over 20%, and that was always really nice for me as a performance engineer to go back to management and said, I need a pay rise, because I just tuned that system, right, by getting the developer to essentially change one line of code. Now, the next trick I'm going to show you is what we call bulk processing. And that essentially will minimize 10,000 inserts to 1 insert. And that may not be, you may not know this technique just yet, but I will explain it to you the other way around. So let's assume you have a table with 10 million rows. And we have some purchases in there, and we just would like to sum these up. So we just want to say, okay, how much money did we make since the 1st of September 2016? What would you rather do on 10 million rows table? Would you go ahead, execute this SQL statement with this where clause to get all those rows back, and then fetch them over the network and sum them up in your application? Or would you rather just apply a SQL function called sum, which does exactly the same thing, but on the database side, and returns you 1 row, and you just get the result? Who is for the first? Okay, the 2 people there on the back. Who's for the second? Hang on. Okay, who has no clue what I'm talking about? Because not all hands went up. Anyway, right. So, well, I would highly recommend the second approach, because the first approach, you will fetch 10 million rows over the network, and you will mostly wait on the network for doing some simple arithmetic that the database could just do on the other side without having to ship all that data back. Now, this is what we call set-based processing, and it's very clear on SQL statements. Anytime you do an aggregation, anytime you do a group by, things like that, you essentially apply set-based processing, or bulk processing. The nice thing is that you can actually also do this on the DML side of things, on the insert side of things. And essentially, what we will do now is we will take the exact same example that we had here, and we will change 2 lines of code. We will change this execute update to an add batch, and then we will have an execute batch outside of the loop. And what will happen here is that we will tell the driver for within the loop to just add the values to an array, which will be 10,000 entries long. And then we will tell the driver in the execute batch, and now just ship this insert statement with the array of values and execute it at once. And so this is where now this big pipe comes in of network round trips. So before we had actually, in this scenario, we had 10,001 network round trips. So 10,000 times we executed the insert statement and then 1 for the commit. In the first example, we actually had 20,000 network round trips because we executed the commit in the loop as well. We didn't really see that because it's all local on my machine. But the other thing that we did tell the database is, please execute the insert statement 10,000 times as well. And the database for 10,000 times does what it does best. It guarantees that you still have access to the table, that the table still exists, that nobody changed the column or data type, etc., etc., etc. So all the good processing that the database does for us to make it a multi-user, highly concurrent system. Now with that one, we just tell it, here's an insert statement, and now just please run it with the 10,000 rows, and then commit at the end. So I go back here in my demo environment, and open that guy. So again, same thing as I said before. Here's this row by row, the very same as we had before. And then, let me go in a bit. And then here we do this add batch. We track the time again. Now, does anybody have an idea how much faster this will be? Like we went from 34 seconds to 14 seconds. Will it be like 7 seconds, 10, 5? Order of magnitude faster. Yeah, perfect. I like that. So let's have a look. Let's see whether this is still up here. Yep. So we execute. We go up here. So same thing here goes on again, 10,000 rows. We go this over here a bit. And we will wait for CPU, just the same as before. It shouldn't really be any different because we execute the very same code, so this will take about 14 seconds. And essentially what we see here is that the CPU time that we use here is, oh, it's already done, is mostly making sure that you still have access to the table and so forth, the processing that the database does for you to execute those insert statements. The second run actually finished in 155 milliseconds. We could not even see it. That demo I can luckily just go ahead and run again because it's fast. So we do this one more time. So again, we will see that we have 100% CPU utilization. Really great. We're executing 10,000 insert statements essentially is what's happening. And then we wait 5 seconds. So here, 11 seconds. We wait 5 seconds. And then we just pump those 10,000 rows over 165 milliseconds. So for the very same workload that we started off with 34 seconds, we actually could tune it to 50 milliseconds, which is quite impressive, right? But it also shows that with a couple of lines of code changed, you can actually dramatically improve the performance of your database if you just know a little bit what's going on behind the scenes, rather than just saying the database is slow. There we go. So generally, just everything that I said, we just pumped everything over there. We executed once. We had no network round trips, nothing like that. We didn't do any unnecessary, not necessary for business processing, but still necessary processing for database concurrency guarantees on the database side. Now, once in a while, the question comes up, okay, so I do this and I insert those 10,000 rows. What happens if one row goes wrong? And the example that I've shown you before, essentially the whole batch will fail and you will have to re-execute all 10,000 rows again. If you do not want it to fail, you can use what we call the DML error logging clause. I believe every database has it by now, where essentially for every row that fails, we will write those values into an error table alongside with the error code that you got the error message and who tried to insert it. And then once the batch is complete, you can query this error logging table, and you can just re-execute that insert and do basically fault detection and mitigation. So you have all the values in there. If you get something, for example, unique key violation, you can check, and you can then in the application figure out, well, should I do an update? Should I just throw the row away because it's already in there or something like that? The data is not lost for you. So that's quite nice as well, and you don't have to restart the batch. The other question that comes up sometimes is, well, when should we actually commit, right? Because we will have to commit at some point to make this data write to disk and be available for other people to see. So should we just commit after 10 million rows, after 100 million rows, and so forth? And the simple answer is whenever your business logic requires you to commit. There are certain workloads where you will have to commit every row no matter what. Typical of these are payment processing workloads. So anytime you withdraw money from an ATM or you have a credit card transaction going on, you really don't want to wait for another 10,000 people to pay as well before your payment is processed, right? And usually the other side, the banks really don't want to lose your payment either. So this is usually workloads where you will just have to commit every single transaction that's coming in. At that point, you start looking into getting faster disks for those redo logs and so forth and try to reduce the latency on the database side of things. But other workloads, they're usually ones that are restartable. You can quite happily have a batch size or bulk size or whatever you call it. So anything typical that you load from files or from queues or something like that, where even if you fail, you still have the data available and you can start again. Those are good candidates for apply something like that. Now, next tip is bind variables. So now we go into the select side of things. I hope I'm not going too fast here. I know it's Saturday morning, but we still have 7 tips to go. So who has heard of bind variables? Oh, wow. Who has never heard of bind variables? Who needs another coffee? Again? Yeah, okay. All right. Fair enough. Granted. So very, very important, bind variables. Again, I'll show you why. So what actually happens when you execute a SQL statement? Well, you toss over a string to the database, SQL statements such as strings, right? So you have something to do with text parsing, with parsing what this SQL statement, what that string actually means, and then you execute it. That's very simple, right? Databases then usually have 2 states of parsing, a soft parsing and a hard parsing. Now, when you go through the stages, essentially what happens is, when you put the SQL over, the first thing we check, or databases check, is it actually valid SQL? Could be any string, right? So we do a syntax check, is the from clause spelled correctly in the right place, etc. Then we do a semantic check. Do you actually have access to the table? Does the table exist? Does the column exist you reference, and so forth? And then we do a shared pool check, which is where we essentially hash that string and then see what it has been executed before. So all databases do that trick. That's usually known as soft parsing. That's essentially just text parsing, string parsing, text parsing, whatever you want to call it. It's very, very fast, takes only a couple of CPU cycles, and it happens concurrently. Each session or each connection does it by itself on the database server. So you not really have any impact by that. You can usually not even measure this other than a couple of instructions on the CPU. Now, if this shared pool check is positive and we see that this SQL statement has already been executed, we will just go ahead and execute the SQL statement. If the SQL is brand new, you have never executed it, this is usually where those cost-based optimizers come in, where we have to go and create an execution plan. So this usually means, what's the best way to access your data? Should we use an index? Should we scan the table? Can we do partition pruning? All the good stuff that databases do since a long, long time to get to your data most efficiently. And then actually something really, really nice, I always found this, then actually, at least in Oracle, we will actually generate assembly code on the fly for you. We have a just-in-time compiler since a long, long time in Oracle. I didn't know this until 5 years ago. So we will actually generate assembly code for you that actually runs these instructions that you have in the execution plan. And we will put this in this shared pool for others to just pick up this code and run it again. However, that is very expensive. That's very CPU intensive. We have to have a couple of logs to guarantee that everything's in place and so forth, that it's still consistent and concurrent and so forth, right? So essentially, hard parsing is what you want to avoid. Now, why does this all matter with bind variables? Because when we come back to a simple SQL statement, if you just have something like this where you say where ID equals 453, we will literally take that string, we'll get rid of the new lines and additional spaces and stuff like that, and then hash it, and this will be the hash that we will generate out of that SQL statement, actually. We call this SQL ID, but it's just a string hash. Now, if you come in and say, well, I execute the same SQL statement with 879, I need coffee too. Semantically, it's exactly the same SQL statement, right? It's like we do the same thing, just with a different input parameter. However, the string hash is completely different because we just do a string hash, and so it looks completely new to the database. And you will essentially run through this hard parse phase yet again, and this code generation yet again. And if you're Java programmers, as most of us in here, you know that you just-in-time compilation, you want to have the optimal just-in-time compilation done once and then just use that rather than do it over and over and over again. Then there's no really good value for that. Now, if you were to use a bind variable, question mark in Java, JDBC, in other programming languages, usually :1 or :name, the very same thing basically. Well, then you can just pass in whatever values to this bind variable, but the SQL ID will always be the same because the string doesn't change. right? So like a tiny little change, but it makes a lot of difference. I'll show you in a second. Funnily enough, when I started in IT, we got it completely wrong. We concatenated every SQL statement together randomly. Performance was really, really bad. And then, this is basically what you will see. So you could also query this in an Oracle database, and you will see those different SQL IDs. Now, here's another example where we use the bind variables. So now, in this example, we select from this table. And then at one point, let's see whether you can see this there. No, I cannot even see it. There at the end, we say where ID equals, and then we concatenate to this I variable, right? So we just basically do, I think, 1,000 selects where we just concatenate the incrementer there, and then we fetch it. And in the second example, we use this bind variable, and we use this set int where we pass on the value for the bind variable. So there's our hard parsing example. Again, just what I've showed you here before. So here we concatenate, right here, and then execute. And here we use this bind variable, and then pass it on right here. Oops, here and here. So we kick this off, and we should see, there we go, we see a lot of CPU. Now this will run quite a long time again. We see actually, if you noticed from before, perhaps not, the CPU profile is slightly different as well. We come very close to this one session bar up there. So we use actually even a lot more CPU. And our session, or connection as we will call it on the app tier, is 100% CPU time bound as well. So we basically now just get those 1,000 rows out of the 10,000 rows, and that will take quite some while. What really happens, well, most of the CPU time will be spent, or is spent, is this hard parsing, this generation, this optimization and generation of execution plans. So here's a little anecdote where people told me in the past, 100% CPU utilization means the system is perfectly tuned. That's absolutely not true, right? It's like we just use 100% of CPU to essentially heat the data center and nothing much more. So this will run for, I believe, quite a minute or so to go through there, just doing this over and over again. There's one other thing for why you should use bind variables, so to consider with bind variables. So there you go, we have finished 67 seconds, we wait 5 seconds, and we are up and running again. We will still see 100% CPU utilization, but this should hopefully be much, much faster as compared to the first one. We see actually we use also a little bit less CPU. The session up there, this is the session up here, by the way, the connection, that's not the CPU itself. So the session is waiting for 100% of its time for CPU, but you're not necessarily using 100% of the CPU on the other side. What that basically just means on the left-hand side, you see that in the background we do the source generation as well on top, which is even more CPU. And there we go, so 28 seconds for the same thing. And this is essentially just what we have done with taking this hard parsing out. It's not as exciting as we did with bulk processing, where we went to a couple of milliseconds, but it's still significantly less overhead and faster execution if you use bind variables. Now, what I wanted to say is, so bind variables are good because we can share already executed SQL statements. We don't have to go through this hard parsing phase. But they are also actually really, really important for SQL injection. Anybody of you guys a Star Trek Discovery fan? All right, well, I hate it too. There's only 3 people, by the way, so just, yeah, I'm a next generation guy. So there was an episode, I think 2-3 weeks ago or something, where they breached the data core via SQL injection 300 years in the future, right? And all we SQL folks made jokes as like, yes, the one thing that in 300 years we still have to deal with is SQL injections, right? We can travel faster than speed of light and so forth. So for those of you who don't know SQL injections, if you concatenate strings together, SQL statements together, like in the example before, I could easily say, rather than passing on a number in this I, where I said where ID equals, and then I had this I concatenated, I could actually easily pass on, say, 1 or 1 equals 1. So rather than having just this one number, I will pass in actually a semantic part of the SQL statement. And then the SQL statement will say, select customer name from customers where ID equals 1 or 1 equals 1. Well, 1 equals 1 is true for every row. And now you would just get all your customer data out of it. With bind variables, that would not happen because you cannot inject this or 1 equals 1 into it. It would just say, that's not a valid number anymore, and you get an exception, and off you go. So that's what's really important as well. Please, if we manage to travel faster than speed of light, let's not make SQL injections our problem at that point in time. Can we all agree? Thank you, yay. Okay, that's so much with the live demos. Now we go through a couple of more tips and tricks here, but unfortunately not enough time to run through all of them. With live demos. The other thing that we sometimes forget is fetch size. So that's not, as I said before, they are not always all applicable, right? So use common sense. But actually, fetch size is a nice way for you to also reduce network round trips if you know how much data you fetch. So by default, the JDBC drivers will actually fetch 10 rows at a time. So when you say result set.next, what will actually happen is that the driver will go to the database and say, give me the values for the next 10 rows, and then the driver will cache it for you, so that for the next 9 times you don't go to the database again, you just go through the cache on the driver. And that avoids unnecessary round trips. Now, if you know that you're about to fetch 200 rows, or you fetch 1,000 rows, etc., and you would like to just minimize that network round trip, you can always set your fetch size to a bigger size for each statement, either for each prepared statement, or I believe also on the connection size. So you can just tell it, okay, for this statement, set the fetch size to 100 or 1,000, and you will just again do this one network round trip rather than many, many, many. Only helps if you know the fetch size, of course, right? If you go, like a lot of times you do a select statement because you want to know how many rows are in there, well, then it's a little bit trickier. So don't just run off and say fetch size from now on is 1,000 for everything. The other trick is, or another trick that we have forgotten is save points. So I mentioned this just before when we did this commit, we removed save points. And essentially what that allows you to do is that you can store or save intermediate states of your transaction. So most of the people don't know that. They only know about rollback and commit. But actually, since a long, long time in the SQL standard, you could just do a couple of insert and updates. And then rather than saying commit, you say save point, and you even give it a name. In this case, Gerald 1. Then you do 2 updates, then save point. And you can go on as long as you like. Those save points will still hit the disk as well. But the nice thing is, if something goes wrong, you can roll back to one of these save points. So you can then say, roll back to save point Gerald 1, and you don't have to execute those first 2 inserts and 1 update statement. So that's just a very nice little trick for not having to redo an entire transaction if you have very large transactions going on and you just have some logical groups of work to be done. You may want to look into save points to make your life a little bit easier. And then at the very end, you would just do a commit and all the save points are removed, etc. So you don't have to worry about that. Well, that's just everything I said. I'm sorry, sometimes I have that. I go off and then I have slides coming up. It's like, oh yeah, right, there was another slide. Tip number 7, KISS. Which, yeah, one of that, or keep it simple, stupid, or keep it simple, SQL. In general, a database performs best if you can put everything into a single SQL statement, in general. There are exceptions to the rule as always, but if you are able to pack everything into a SQL statement, into a single SQL statement, you will get the set-based processing that the database does for you. So all the optimization kicks in, etc., and you execute this only once, and you get all the data as fast as possible. Now, here's an example where somebody went off and wrote a very nice SQL statement where all they wanted to do essentially was to concatenate values of rows via a semicolon. So just go through all those rows and then just give me one long string back with semicolon delimited. Unfortunately, that person did not, I mean, he was quite sophisticated in writing SQL code. It's a lot of SQL code. But he didn't really check the functional reference, the SQL reference, because he would have found that he could have just used the list ag function and reduced the SQL statement to this. So that's exactly the equivalent to that guy over there, just a lot less code. The other nice thing is if you keep your SQL simple, it's easier to maintain for you, usually, or whoever comes after you. and it's also quicker to optimize as well. So because you don't have to read, like in this case, we read from the same table twice, and then we connected, hierarchical structure, etc. Those are just all different paths of optimizations that the optimizer has to consider. While here we essentially just read the table once, and it was much easier for the optimizer, much faster, much less permutations for the optimizer to come up with an optimal plan. So the other nice thing about Keep It Simple SQL is that since a couple of years now, since 2011 standard, I believe, we have something that we call Common Table Expressions, CTEs. Or we in Oracle, we call it with clause. And that's exactly used for when you have a SQL statement where you have to go back to the same table a couple of times. You join via different values to the same table or something like that. What the databases would usually do is they would run in there and they would query the table multiple times if you instructed it to do. With this common table expression, you could actually execute that statement once to begin with of the SQL execution, and then a database caches the result in memory for you, and then it will just go back to this memory structure. So essentially, you don't read the table multiple times, and you will just go straight against memory once it's executed and cached. It also, again, makes your SQL much, much readable. So what we do here is we just have a simple select where we get all active users from the active user table, and then we join this against the personal and business accounts. Before we would have to join for personal accounts, we would see, hey, active user, are you personal account? Hey, active user, are you business account? Here we just select all active users first and then just join against this memory structure on both tables. And again, it makes it more readable as well. And then last on this one is that sometimes people ask me, can you do recursive SQL statements? The answer is yes, with those common table expressions as well. So in this case here, we have a nice little example how you can do a recursive SQL statement in the Oracle database. That syntax pretty much works again in every other database because it's SQL standard. Tip number 8, parallel queries. Now, the way how databases get to this highly concurrent execution is that they, for each connection that we establish as a programmer, which is usually a very tiny, lightweight Java object on our side, or any kind of whatever programming language you use, an object on our side, you actually end up getting a dedicated server process, so really a Unix process, on the database side executing a SQL statement. And therefore, each connection has their own processing, and they take up to 1 CPU. So that's really nice if you have many, many different transactions coming in or tiny little SQL statements coming in for fetching a couple of rows, etc. You always have your dedicated CPU, essentially, your dedicated process to execute that. And that's how you get 10,000s of those sessions running concurrently. If you, however, have one session and you want to query through 100 terabytes or 500 terabytes of data, you may come to this situation where you go like, great, I have this one session, this one connection, and we are just sitting here on one CPU and doing nothing, and I have 63 other CPUs sitting there. Can we not just use them? And this is where parallel query come in. They're actually rather easy to use. All you have to do is you add this parallel hint in one way or another. And now the database will go off and use all the CPUs available on the system. There's min and max that DBAs can tune so that you wouldn't overload the system. And then you actually use the full power of the machine. So that's very nice if you want to speed up long-running, very data-intensive queries instead of tiny little transaction queries. The one important thing about this is it's not a universal performance booster. So don't, as I said before, common sense, don't just run off and say all our queries run parallel now. You don't want that for short-lived transactions or queries anyway, because there's no point in you in spinning up many, many different parallel threads to just come down to one again. You would basically just waste time on the overhead of doing that. For anybody of you who has ever dealt with MapReduce and Hadoop, very similar scenario there. It's also not that it necessarily speeds up everything. So it's usually really in the data warehousing environment where you have massive amounts of data that you go through, but few connections to the database. If you have many connections and everybody wants to run in parallel, you will just starve on CPU resources. They will just start fighting for those CPU resources. Tip number 9, explain plans. So this is what I said before, like whenever you execute and optimize a SQL statement, you will come up with those execution plans, or the database will come up with these execution plans of how to actually access the data. Now you can actually look at these execution plans or explain plans in a very simple way, just to give you an idea of what's actually going on and whether it looks correct. It doesn't necessarily mean you have to be or you want to be a full SQL tuning guy, but if you have a slow-running SQL, you can very easily just take your SQL, throw an explain plan for on top of it, literally 3 words, and then execute this select, as we do here with this table, with the statement before from the KISS. So literally 3 words before, and then we do the select, and then you will come up with something that looks like this. That's the explain plan for that SQL query. And again, you don't necessarily have to be a SQL performance tuner and now say, okay, I know exactly what a hash join right outer means, or what a hash join, index full scan means, and so forth. But it gives you already a couple of hints of whether you're on the right track or not. So in this scenario, we see here in red, we do a table access full of those all active users. And the database tells us already, well, there's 100 million rows in that table. And we're retrieving about 3 gigabytes of data by just scanning that table. Not over the network just yet, but the database has to read 3 gigabytes of data from the disk. And then we essentially just join it together, and the end result, when you look at row number 0, the select statement, you still get 100 million rows back there, and you actually return 39 gigabytes of data in combination with the all active users joined by every single row of the other table. So you get a lot of data back, a lot of rows back that you probably don't want or need. And in this case, all that there was missing was an index on that table, on that column. Then we wouldn't have to do this full table join and so forth. So explain plans are a nice, easy way to just have a look, see whether it feels right. Right? If you go like, well, I really didn't want 100 million rows back, that's a lot, maybe I just wanted 3 back, then perhaps something is wrong down the line. And they're very easy for you to just create with any SQL tool that allows you to run some ad hoc SQL statements against the database and so forth. The last tip is the wait events that we have essentially used before. Now, this is Oracle database specific. There aren't many other databases out there that have this tracing in place, but if you happen to have an Oracle database, just like the tool that I showed before, it essentially executed select statements itself to retrieve all the wait events for other sessions, and it looks something like this, actually. So there is a view called $session wait, and we just said, please give me every session ID, the event, the wait event we're waiting on, and the wait class from every session where the wait class isn't idle. So we calculate idle as waiting as well. We're waiting for the application to give us something. And that will essentially give us, in this case, it gives us back, okay, 3 sessions here are waiting on user I/O. We're reading a lot of data from disk. While the others are actually, you see here on the wait class application, they are actually all waiting for an application to finish. So what we did here, or what I did here essentially, is I locked 1 row with an update, I didn't commit, and then had a couple of other sessions go after updating the same row. This would show up at this NQTM contention or TX contention, depending on what lock you apply. So we're just waiting for the lock to be removed. And then I had 3 sessions that just read a lot from disk. Now, why do I tell you this? Because with a very simple way, with just knowing a little bit of SQL, you can actually just select yourself or see for yourself what your application or the SQL on behalf of your application is actually doing on the database side. And you know, this whole talk was about to essentially take this black box database thing away. Databases are not that complicated, at least to get a feel and figuring out am I on the right path or not. Wow, 7 minutes to go, perfect. We have 5-minute Q&A as well, maybe 6. If you want to know more about everything I've just said, if you actually look at the Oracle database documentation, you will find a performance tuning guide. That is a really, really good book in general if you're into performance tuning. This has been written since over 20 years from some of our brightest guys on how to do systematic performance tuning. Some of those folks that we still have in Oracle that are there since literally 40 years of existence that can tell you things about how systems operate that I never ever learned anywhere. So that's a really good book if you like just to know more about performance tuning in general and of course of database performance tuning. If you want to start your career as SQL tuning expert or a SQL security expert preventing SQL injections, SQL Tuning Guide is a really good book as well that tells you all about how to tune SQL statements and so forth. We do have a database development guide that takes you through a couple of those concepts and philosophies, how you want to architect your application for best performance. So it will cover things that I've shown you before, like you don't want to commit every row if you don't have to, and so forth. And then for the Java folks specifically, but also all other programmers out there, we have those developer guides for the programming language specific driver as well. So if you want to know more about how you can tweak your JDBC, but also your Python driver and so forth, you will find the JDBC, your Python developer guide and so forth, and also the universal connection pool, our own connection pool for JDBC. If you want to run these examples that I've shown you yourself, you can find them on my GitHub and just go to this supercharge your code, where you have exactly that one repo that I just showed you with these 3 files and classes in there, where you can play around with it a little bit yourself as well if you would like to. And with that, I would like to thank you very much for your attention. I know it's Saturday morning, and I know a lot of people, including myself, need some more coffee. We have another 5 minutes if there are any questions. Otherwise, I give you 5 minutes of your Saturday back. Thank you. One question there. Do we have a mic by any chance, a microphone, or otherwise I'd try? Oh, there we go. Question right here.
How would you go about refactoring a complex query? How to verify the same operation after the refactor?
How to refactor a complex query that does you still achieve the same result. So in general, what you always want to make sure is before you refactor the query, take an execution or explain plan to see what happened before. Also I would recommend take the output of a SQL statement and then compare whether you still get the same output afterwards as well. The operations will change, so sometimes when you see, okay, we want to get rid of this operation because that, like a full table scan and so forth, you will then be able to compare. No more questions? Great. I actually didn't try to learn thank you in Serbian. How do you say thank you in Serbian? Hvala? Hvala.